So let's think about where we've been so far. So we start with our linear layer, right? Our linear function. And remember, that's just w dot x plus b. So that's us pairing together the entries of our weight vector and our features, multiplying the pairs, and then adding up the product plus our bias. So this gives us an output between negative infinity and positive infinity, right? And that's then compressed down using the sigmoid function to a value between 0 and 1. And these two layers is essentially, right, what our neuron predicts. And we can summarize that with this. So this is just, putting this guy into the parentheses and then applying the sigma function. So these are equivalent. They're exactly the same. Now the next thing we did was we said, all right, well, we want to perhaps learn what is the correct parameter value, like what is the W that best predicts our data. And the way that we do that is by looking at past data, our training data, right? We said that, these graduate students recorded, both the cell area, how big these potentially cancerous cells were, and also whether or not they were cancerous, right? And we have like a 1 for they were cancerous and like a 0 for a cell that was not. And then what we did was we said, okay, well, how well does our hypothesis function, how well does this prediction come to the actual value when we use a specific weight of, say, like -2? And the way that we determine how well or how good a job our predictions or a neuron is doing is by using the squared error, right? Where we get back a prediction, like a value between 0 and 1, and then we compare that with the actual value. So if our hypothesis was or our prediction was 0.1, and the actual value was 0, then this would be like 0 minus 0.1 squared, and that would be our squared error. And that's how good a job our neuron is doing on predicting whether or not this first observation was cancerous. Okay? But really what we wanted to do was we wanted to perform this across all of our observations, right? Because bigger sample size. And we do that simply by taking our entire data set, calculating the squared error for each observation, and then adding up those squared errors. And that gives us, right, the sum of the squared error. And what we said was, in order to find the best W1, we simply try a lot of weights. So we try the weight at -2 and see what is the squared error or the sum of the squared errors when our weight is -2. Then we go to the next one. What is the sum of the squared errors when our weight is -1.8? And so on 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 until we then see, okay, well, we tend to do the best. In other words, we have the lowest sum of the squared errors when our weight is -0.2. Now, this approach works fine when we are only working with a single parameter, like that single weight that we're multiplying by our cell area to then ultimately get an output from our linear layer and then our activation layer. But if we are working with lots and lots of different parameters, by that I mean like thousands, then just trying every single value, potential value for every single weight is not a good technique. It will just take way too long. So we need a more efficient approach. So this is one thing that people have noticed. It's pretty cool. What they've noticed is if you try a weight, like let's say -2, and this is pretty far away from our minimum, okay? And if you just try this one weight, what you can also notice is that the slope is pretty large, right? It's -40. But the closer we are to having a weight that produces this minimum sum of squared errors, the flatter the slope, right? The smaller the slope. Here's only -24, okay? And then the further away we get in this direction, it's the same thing. So instead, what we could do is just try like a single weight, like let's say -2, and then we can, for our next guess, say, okay, if we're far away, if this slope is really, severe, then that means we must be far away from the minimum, and so we should update this weight a lot, right? So our next guess should be pretty far from what this first guy was. If instead we are like close, or we have a flatter slope, that means we're probably pretty close to the minimum value. And so we should not update our weight as much. We should take a smaller step size. So let's turn this into a formula, right? The formula is essentially take a guess, right, of a weight. Let's say set it to -2. Calculate the slope of the sum of the squared errors at that weight. Here it's -40. And then use this slope to guide the next weight that we're going to choose. So what does that look like? Well, we can start it, maybe it looks like this. So we choose a weight of -2. The slope at that weight is -40. And then to update this weight, we simply do W1, our new W1, is going to equal our old W1 plus the slope at that old W1. So if our first guess was -2, our second guess is going to be -42, which is not good. This is not good for two reasons. One, we moved in the wrong direction. Okay, so we started here, we went this way, not good. The second thing is we took an enormous step size, like we moved drastically. So we want to change, we want to fix those two problems. So the first problem about moving in the wrong direction is not so difficult. Instead of doing W1 plus the slope, let's do W1 minus the slope. So we'll move in the negative direction, in the opposite direction of the slope. So now we'll go from -2 to 38. So at least we moved in the correct direction. The problem is that we way overshot the mark. So this we can also affect. We can, fix this by, instead of moving by the value of the slope, by moving by 40, let's move by just a fraction of that value. So we'll move by 0.01 times by 40. Let's see what this does. So we start at W1 equals -2. We then have the slope at that value. And our next weight is going to be the original minus, some small number times by the slope. And what does this give us? Well, this gives us -1.6. That's a pretty good next guess. You can see we're moving in the correct direction. And if perhaps we tried this again, so let's say we wound up here. Well, this would be -1. Let's just do this again. So let's say we wound up here to -1. The slope at this is -24. And then we do W1 minus 0.01 times the slope at W1. Let's see what that gives us. -0.76. So you can see we continue to kind of move in the right direction without overshooting the mark, which is what we want to do. Okay? So this is like a more efficient way to descend along our cost curve. Now, just to show you this in action and how well this can work, I wrote out some functions for us. We can try this on our real data. So this is our paired data again, right? These are all the observations of our cancer cell. I'll show you. We get a bunch of them. Actually, let's use, this is not the best. Let's use this. Okay, better. All right. And then what we'll do is we defined basically our hypothesis functions again. So this is our linear function. This is our activation function. This is the sum of the squared errors. And then I wrote some functions that's going to calculate the slope of the sum of the squared errors, right? It's going to calculate this slope for us. So that, right, we'll learn about that later on. It's called the derivative. But for right now, this works fine. We can just take my word for it. So we have W1. And then this is the slope. So this is the sum of the squared errors at W1. Okay? And then what we can do is we know that our formula is the new W1 equals the old W1 minus 0.01, say, times by that slope. And it breaks. Because W1 is not defined, W_1. Okay? Cool. All right, so we take a step. And what we want to do is keep taking steps. So we don't do this just one time. Let's do this multiple times. So we start here, and we're going to say W1, let's maybe refactor this a little bit. Right? If this is our next step, right? So we start at W1 equals -2, and then our new W1 is going to be, our old W1 minus this 0.01 times by the slope at that value. And instead of just doing this once, let's try this like 10 times. For I in range 9, I think that does it 10 times. We will do this, and let's maybe print out the W1 each time, and then we'll see this end result. See that? This is pretty cool, because we're starting at a value maybe far away, -2, and then we get closer and closer and closer until in just 10 steps, we're getting to that value of -0.2 again. So the reason, again, why this works is because we noticed that, we can move in proportion to our slope. So we choose a random value, calculate the slope at that value, and then move by a fraction of that slope. As this slope gets flatter, we take smaller steps. And that's exactly what happened. Let's take a look. Our first step size was 0.4, but then this was a little bit smaller. And then down here, look at this. Now we're really moving slightly, okay? Until we're like quickly approaching or edging up against that minimum value. We can really see this if we store this, okay? So I'm gonna now, instead of printing out each of these values, right, we did here, let's actually maybe store these W's in a list. So that's what I do down here. Where do I do it? Okay, right here. Okay, so I'm going to start at -2 and then just apply that exact same formula, right? I call this 0.01 the learning rate. And this 0.01, right, but this is just getting us to move at a fraction of the slope. So we start at that original weight, we do that formula of minus times by the learning rate, minus the learning rate times by the slope at that current weight. And using that formula, we get to the new weight. So let's apply this, and then let's calculate the sum of the squared errors, and you can kind of see what happens, right? This is our first guess. Our first guess was -2. Then this was our second guess because we used this old formula. Then we did this, and our slope got less steep. So that means our next step got less severe or less large. Then this is flatter. So we move less, and we're flatter and flatter and flatter and flatter. So this is only 10 steps, right? We only did this 10, 11 times. And in those 10 steps, we got to -0.27, which is what we saw in the last lesson. So you can see that this is a really, effective way. Instead of trying them all, we're using the slope to guide us, okay? So that formula, again, is this, that our weight is going to be our new weight. The way that we're going to update this weight, we start with something random. We set this 0.01, this fraction, we call this the learning rate, right? That's going to effectively make sure we're not overshooting the mark. And we're going to say our new weight is going to be our old weight minus the learning rate plus the slope of the sum of the squared errors at that weight, right? And by just doing that, what this does is it allows us to, use this slope to tell us how big our step size should be. And because when we are far away from the minimum value, or the parameter that minimizes our cost function, this slope is relatively large. But as we approach that parameter value that minimizes our cost function, the slope gets less and less large. That means that we're not taking as large steps. We're kind of creeping up on the parameter value that we want, and we're not overshooting the mark. So that's why this is, an effective technique, and this is called gradient descent. And I just wonder, I guess I didn't write it down. Here it is. This is exactly what that is, okay? Mathematically, these two statements are equivalent, all right? This is how we did this in code, and this is what gradient descent looks like in mathematically. where we say the next parameter value is our current parameter value minus the learning rate. This is the letter eta. Eta, that's not important. Times by the slope at that parameter value. And we just keep applying that, okay? And you just say like, okay, you apply that like 100 times or something, and that's it. And that will help us find the parameter value that minimizes our cost curve, and allows us to do so in such a way that we're not simply trying them all, but rather when we are far away from the parameter value that minimizes our cost curve, we take large steps. And when we are close to that, we take smaller and smaller steps because the slope is smaller and smaller. So that's it. This is gradient descent. And I encourage you, to go to the lesson and to play around with this, because it kind of is fun to see this in code. All right, next up, we will move into using PyTorch to train a neural network. So that'll be really cool. All right, see you there.